Hello class 12. As you all know that we were discussing about the chapter chemical kinetics. Today we are going to discuss about a very important concept. Keep in mind the concept of activation energy. Now normally in exam the question comes, what is activation energy? What is Arrhenius equation? Or what is collision theory? So we are going to discuss the theoretical portion first, and then I will explain you how to see log table and how to solve the numericals. Before doing that, we will discuss the theory portion first. Now we all know that reactions are those in which the concentration of the reactant decreases, whereas the concentration of the product increases. The speed with which a reaction takes place is called rate of reaction. So rate of reaction is simply defined as change in concentration with respect to time. It has been found that initially the rate of the reaction is high. Initially the reactant reacts at a faster rate, and later on it has been found the rate of the reaction becomes slow in some cases. Now, what is activation energy? When the reactant reacts, you have seen that in some of the cases we have to supply the energy from outside. That is the case of endothermic reactions. Endothermic reactions are those which require heat to the reaction to occur. So, let us see now graphically what is the meaning of activation energy. Activation energy is the extra amount of energy which is required by the reactant to get converted into product. So activation energy, extra amount of energy required by the reactant so that their energy becomes equal to or greater than threshold energy so that they get converted into products. So let us see a graph. We have a very simple graph between potential energy and reaction coordinates. This is reaction coordinates versus potential energy. This is reactant and this is product. We know that a substance or the reactant react to form product. Reactants are always of high energy and the product should be of lower energy, because lower energy leads to stability. Now, reactants have to convert into product. So when the reactant molecules react with each other, they have to cross energy barrier. This energy barrier is called threshold energy barrier. So threshold energy is the amount of energy which is required by the reactant to get converted into product. So reactant, if they want to get converted into product, then they have to cross this barrier. Now, reactant has this much amount of energy, that is their own energy, but they need this extra amount of energy to cross this barrier, this threshold barrier, so that they get converted into product. So this barrier, this one, is called activation energy, written as EA. So activation energy is the extra amount of energy which a reactant required to get converted into product, or the amount of energy required by the reactant to cross the energy barrier. So activation energy, amount of energy required by the reactants to cross the energy barrier. So that is what we call activation energy. So keep in mind, activation energy is the extra amount of energy which is required by the reactant to get converted into energy, to get converted into product. So we say activation energy equals to threshold energy. That means energy from here to here is threshold energy minus energy of the reactant, initial energy of the reactant that the energy reactant already has. So from here we take this is threshold energy minus potential energy of reactant. So that is the concept of activation energy. Now, normally we have seen that a catalyst, when a catalyst is added, the speed of the reaction increases. A catalyst is a substance which do not undergo chemical change in itself, but it increases the rate of the reaction. Now the question arises, what is the role of catalyst? So here, role of catalyst. A catalyst lowers the activation energy hence more and more reactant get converted into product. So a catalyst, it provides the surface for the reactants to occur, and the major function of the catalyst is to lower the energy barrier. Now you can see, for the reactant to get converted into product, initially the reactant have to cross this barrier which is of greater energy, but when a catalyst is added, the barrier, potential energy barrier, it decreases. When the barrier decreases, now more and more reactants they get converted into product. Hence, the rate of the reaction increases. This is without catalyst. And you can see this curve, it is with catalyst. So, we can simply say a catalyst, it lowers the energy barrier. That is why more and more reactants, they can be easily converted into product because they require less energy to cross the barrier. Hence, they can cross the barrier easily, get converted into products. So that is the concept of activation energy. Now, let us see what is the effect of temperature. It has been found that in most of the cases, the rate of the reaction becomes double for each 10-degree rising temperature. Arrhenius was the first scientist who gave the relation between the rate constant and temperature with activation energy. So, now let us move towards Arrhenius equation. This is activation energy. Now, Arrhenius equation. Keep in mind one very important concept. The rate of the reaction is almost double for each 10-degree rise in temperature. It means when this reaction occurs, let us take a reaction is occurring at 298 Kelvin. When we increase the temperature from 298 Kelvin to 308 Kelvin, you will find that the rate of the reaction, means speed of the reaction, it becomes double. That expression, that increase in rate of the reaction was explained mathematically by Arrhenius. So Arrhenius equation, K is equal to A e power minus EA upon RT. This is called Arrhenius equation, where K is called rate constant, A is known as pre-exponential function, or sometimes it is also known as frequency factor. EA is activation energy and T is temperature and R is gas constant. So this is an expression which correlates rate constant, activation energy and the temperature, which explain the effect of temperature on rate of reaction. This is called Arrhenius equation. Now, let us see how to use this equation. We know K is equal to A e power minus EA upon RT. Let us take log both sides. Log, that is natural logarithm, ln K is equal to ln A e power minus EA upon RT. So ln A is equal to ln A minus ln e power minus EA upon RT. And we know that when we change ln into simple log, this ln e, it is 1, it comes here comes plus sign. So ln k is equal to ln a minus ea upon r. Change natural logarithm to simple log. 2.303 log k is equal to 2.303 log a minus ea upon r. So this equation changes now. Log a is equal to log a minus ea upon 2.303 rt. So this is the mathematical form which is used for Arrhenius equation. Now, where log k is rate constant, A is pre-exponential frequency factor, E activation energy, RT constant, R is gas constant and T is temperature in Kelvin. Now, let us suppose we have two equations. Let us say a reaction has a rate constant K1 when temperature is T1. So log K1 equals to log A minus EA upon 2.303 RT. This is equation number 1. Similarly, when the temperature of the reaction changes to T2, then the rate constant is K2. So log K2 is equal to log A minus EA upon 2.303 RT2. This is equation number 2. Subtract equation 1 and equation 2. So when we subtract, we get log K1 minus log K2 equals to, it got cancelled, minus EA upon 2.303 RT1 plus EA upon 2.303 RT2. So we get log K1 upon K2 because here we have minus, so log K1 upon K2 equals to EA upon 2.303 or 1 upon T2 minus 1 upon T1. If we take here reciprocal, we change the sign. So log K2 upon K1 is equal to EA upon 2.303 or 1 upon T1 minus 1 upon T2. Keep in mind, T1 is initial temperature and T2 is the final temperature. This is known as Arrhenius equation. So we have seen there are two forms of Arrhenius equation. One is K is equal to A e power minus EA upon RT, and the second is log K2 upon K1 equals to EA upon 2.303 or 1 upon T1 minus 1 upon T2. R is a gas constant whose value is 8.314. Keep this thing in mind. So that is what we have, Arrhenius equation. Now, when we plot a graph between log K, that is logarithm of rate constant, and 1 upon T, we get a straight line having a slope minus EA upon 2.303 R. Now this one we have derived, we know K is equal to A e power minus EA upon RT. You have seen that when we solve this, we were getting log K is equal to log A minus EA upon 2.303 R into 1 upon T. So when we plot a graph between log K versus 1 upon T, this one will be the slope. So slope is minus EA upon 2.303. Now that's all for the Arrhenius equation. Now we are moving towards the last topic of the chapter, and that is collision theory. Now what is this collision theory and what it has to say? Of course we will discuss numericals. Numericals we have to do. We left with few numericals of Arrhenius equation. Now when we talk about the concept which is called collision theory, let us see what is this collision theory. Collision theory, it simply states only those reactants get converted into product which crosses two types of barriers. Keep in mind, we have two kinds of barriers. First barrier is called activation energy barrier, and second is known as orientation barrier. So collision theory, it says only those reactants get converted into products which crosses two types of barriers. First barrier is called activation energy barrier, and second is called orientation barrier. It has been found that in most of the cases, when we increase the temperature, the rate of the reaction does not increase. In that cases, we say the orientation of the reactant is not proper. It's a hypothetical concept, but it is supposed that the molecules which are reacting together, they must have a proper orientation. First barrier we know, activation energy barrier, which simply indicates only those reactants get converted into product which crosses the threshold energy barrier, means which have a minimum activation energy. So first is activation energy, that is also called we say energy barrier. Second, orientation. Let us take a simple example, A positive and B negative. Let us take another molecule, C negative and B positive. When these two molecules come closer, you can see A, B, C, D, negative, negative. When negative come close to negative, they have similar charges, so they do not attract each other. We say they do not undergo effective collision, they do not form product. Why? Because they are not properly oriented. We say no proper orientation. But when A positive, B negative come close to B positive, C negative, then you can see here B negative, B positive. They have opposite charges. So when they come close to each other, they start attracting each other. If the new forces of attraction are greater than old force of attraction, then it easily forms product. And we say this molecule is properly oriented. So keep in mind, any reactant to get converted into product, the reactant molecules have to cross two barriers. First, activation energy barrier, and second is called orientation barrier. So reactant get converted into product when they possess or when they cross both kinds of barriers. So with this, the chapter is over, but we will discuss numericals. Now you all are advised to revise the chapter thoroughly. If you find difficulties, contact us, but work hard. It's very important. Thank you and have a nice day.